I wanted to recap what we were talking about in the last video. So the result that we got, we took our original loading here on the left and then found our equivalent loading here on the right. And essentially what this is saying is that whether we apply this force couple system at A or this force couple system here on the right at H, these two systems are equivalent and they are the same. They have the same effect on the object. The next item we're going to cover is chapter 4, and we're going to talk about equilibrium of rigid bodies. So equilibrium of rigid bodies. We've previously talked about equilibrium, but when we talked about equilibrium previously, we were talking about equilibrium of points. And when we think about points, we never had to consider moments. But now that we're talking about equilibrium of rigid bodies, not only do we have to say the sum of the forces is equal to 0, but we also have to show that the sum of the moments is equal to 0. So for problems that are in 2D, which is how we'll start, we have 3 equations, which is the sum of the forces in the x direction is equal to 0, the sum of the forces in the y direction is equal to 0, and the sum of the moments in the z direction, that x is sticking into and out of the page, is equal to 0. Most of our problems that we solve for using equilibrium of rigid bodies, our rigid bodies are attached to either the ground or the wall or some other objects, and they're attached somehow. And in order for us to solve these problems, we need to free those rigid bodies from the attachments that they have or the connections that they have. So the first thing when we talk about equilibrium of rigid bodies is to look at our different supports or connections. This table is in your book, but I wanted to show it to you here. So one type of support and connection we have here is rollers or rockers or a frictionless surface. And the reaction, so how we're going to replace this support or connection with a force in our free body diagram, is going to be a force where the line of action is perpendicular to the surface. And that's because rollers, rockers, and frictionless surfaces only prevent motion in the direction perpendicular to the surface. They don't prevent us from moving back and forth. They only prevent us from moving up and down. If our connection is a short cable or a short link, the force we're going to replace that with is a force in the direction of the line of action. And remember, with a cable, we cannot push with a cable. You can't push with a rope, you can only pull with a rope. So if we have a cable or a rope, it is always, our arrow, our force is always going to go away from the object. If we have a collar or a frictionless pin and slot, the force that we're going to replace that with in our free body diagram has a line of action that is perpendicular to the rod or slot, because if we think about this pin and slot, this thing can still move back and forth this way. The only way we are preventing action is in this way and this way. So the only force that we'll draw in our free body diagram is here in this direction. If we have a frictionless pin or hinge or a rough surface, we're going to have a force of unknown direction, which we could solve for that way, or we can say that we have an X and a Y force. So we're going to replace frictionless pins or hinges in rough surfaces with a force with an X component and a force in the Y direction. The last type of connection we're going to have in 2D is a fixed support. And our fixed support is going to have that X and Y force. So we have a force in the X direction, we have a force in the Y direction, but we will also have a moment or couple. And the reason we have all three of these, so the two forces and a couple, is because a fixed support prevents us from moving back and forth in this way, so we can't move that way. It prevents us from moving back and forth in this direction. It also prevents us from rotating. So it prevents movement in those directions. Therefore, it is applying forces in a moment. Let's go through this with an example. This example is number 4.7 in the book, and we'll go through this 2D equilibrium problem using the methods that we will use for all of our equilibrium problems. This problem gives us that A is equal to 10 inches, so this is equal to 10 inches here. We're asked to find the reactions at A and B, and we need to make assumptions. So we're going to assume that we are in equilibrium. We are going to assume that the objects or body is weightless. And lastly, we're going to assume that this roller at A and the pin at B, so roller at A and the pin at B, are both frictionless. And that's a fair assumption because we haven't really talked about friction yet in this class. So we're asked to find the reactions at A and B. So A is a roller. So we're going to have a force perpendicular to the surface. So we're going to have a force in the y direction, AY. B is a pin. So we're going to have a force in the x direction, Bx, and a force in the y direction, By. So we have three unknowns, A, Y, Bx, and By. So we need three equations to solve for those three unknowns. But before we can solve for our unknowns and write our equations, we need to draw our free body diagram. I'm going to start drawing my free body diagram by freeing the body from its connections at A and B. So I'm just going to draw the object here. Once I free the body and I've drawn the body, I'm going to draw in all of my known forces and my dimensions. So our first step is free the body from supports. And our second step is to draw in our dimensions. So we have This is definitely not to scale. We have 8 inches, 10 inches, 6 inches, and 6 inches. Our next step is to draw in the known forces. So we can see we have these different red arrows here. So we have a force down here, 40 pounds. 50 pounds, 30 pounds, and 10 pounds. Once we draw in our known forces, we're going to replace the supports with our unknown forces. So at A, I'm going to have a vertical force here, AY. And at B, the pin is going to be applying a vertical force, BY, and a horizontal force, BX. Also, in my free body diagram, I need to include my axes. So let's go ahead and draw in an X and a Y axis here. So this is my X direction, maybe my origin's over here, so then my Y direction will be there. Now that we have drawn our free body diagram, we are ready to write our equations. We can start with our sum of the forces in the X direction is equal to 0. And I see I only have one force in the X direction, that's Bx. So I have Bx is equal to 0. Next, I can sum the forces in the Y direction. It's equal to 0. So I have By minus Ay minus 40 minus 50 minus 30 minus 10. Next, I'm going to sum the moments in the Z direction, and I need to choose a point to take the moment about. I like to take the moment about a point that my unknowns are going through. So if I choose a point that I have unknowns going through, then I eliminate some of the unknowns in my equation. So let's take the moment about point B. So I'm going to write a little note for myself over here. So when taking the moment, choose a point that has unknowns going through it. That way we have fewer unknowns in our equation and we just have less algebra when we're solving. So when I'm solving for the moment about point B, which I'm just going to highlight that moment, or that point is this point here. So I have AY, it's going to create a counterclockwise or positive moment about B. I have a moment arm of 12. And then that 40-pound force is going to create a moment about B. And I have a moment arm of 6, and that is a positive moment. That 50-pound force, remember using the principle of transmissibility, I can slide that force so that it goes straight through B. So that 50-pound force has a 0 moment arm, so it will not create a moment about B. Then I have my 30-pound force. is going to have a moment arm of 10. And that's going to make me rotate clockwise, so that would be a negative moment. And then I have that 10-pound force, which will have a moment arm of 18. That will also make me want to rotate clockwise, so that has a negative moment. Note, we could have solved this problem using cross products, but we would have had to take the cross product for each vector to solve the moment that each vector or each force creates about B. So in this instance, our right hand method, or our more intuitive method, really helps us kind of have to write fewer equations. So once we have our equations written, our next step is to solve those equations. So I'm going to start with my sum of the forces in the x direction, and that gives me the Bx is 0. So this is my sum of the forces in the x. If I use my sum of the moments about B, I can solve and get Ay. I have 30 times 10 plus 10 times 18 minus 40 times 6. That's all divided by 12. And I get Ay is positive 20 pounds. And when I'm solving for the sum of the forces in the y direction, I get that By is, so I have minus 20, minus 40, minus 50, minus 30, minus 10. So I get a positive 150 pounds. And just a quick note about this positive Ay. So positive here means that I drew my vector, I drew my unknown in the correct direction, not that Ay is in the positive y direction. So positive here means free body diagram vector is in correct direction. Not that Ay is in positive x, or sorry, positive y direction. So it's really important that we understand this. So if you have questions about this, how getting positive values means that we drew the vector in the correct direction and doesn't tell us that it's in the positive y direction. Please ask questions about that, because we're going to be kind of using this idea as we move forward. So that's that for that video.